Hello and welcome to today's webinar organised by Spectra Analysis. My name is Jessica Allerton, Associate Editor of The Analytical Scientist, and I'm delighted to be the moderator of today's event, which is called DiscovIR-GC Detector, Integration of GC-FTIR and MS as a unique tool in the identification of positional and structural isomers. Our first speaker today is Nathan Hawkins, CEO of Spectrometrics Limited. Nathan managed a metabolomics core facility for 14 years before moving into a hybrid commercial role. In 2022, he established Spectrometrics to bring new and emerging analytical technologies to the UK and Ireland. Our next speaker is Tracy Philpott, Senior Applications Chemist at Spectra Analysis Instruments. Tracy's experience has spanned the textile, polymer, tyre and pharma industries for various companies. This includes Morton International and IRIX Pharmaceuticals. Our speakers will be on hand to answer any questions that you may have at the end of the presentation, but please remember that you can submit questions at any time throughout the webinar. Okay, we are now ready to start the presentation, so I'll hand it over to our first speaker, who will take over proceedings until the live Q&A. Nathan, over to you.
Hello and welcome to our webinar. I'm Nathan, and today I'll start by introducing DiscovIR-GC technology before handing over to Tracy, who will look at using the DiscovIR-GC for the analysis of fentanyl analogues. Spectra Analysis Instruments is based in the United States, with R&D, production, finance and admin being based in Marlborough, Massachusetts, and applications, service, sales and marketing supported from the Greenville, South Carolina office. The DiscovIR-GC is a hyphenated solid-phase GC-FTIR instrument that has been adopted by law enforcement, customs and border agencies worldwide for the analysis of illicit drugs, including novel psychoactives, synthetic cannabinoids and other designer drugs. These pictures show typical DiscovIR-GC configurations with the heated transfer line from the gas chromatograph, vacuum chamber and dewar cap highlighted. Despite being a mature technology, DiscovIR-GC is a relatively new hyphenated technique to most chromatography and mass spec users. It is therefore useful to introduce concepts in familiar terms. Separated components are deposited onto a reusable cooled zinc selenide disc, which is about the same size as a compact disc or DVD. Under default deposition speeds, a full scan infrared spectrum is acquired every 0.6 seconds. Up to 40 hours of chromatography can be deposited in a spiral track, which is recorded in a similar way to the groove on a vinyl record. The 3D data structure is similar to GCMS, comprising a base peak chromatogram and high-resolution structurally informative FTIR spectra for each scan. To the user, the main noticeable difference to GCMS is the routine use of contour plots in data exploration. As with GCMS, spectral libraries can be searched, though the higher selectivity and specificity of solid-phase IR spectra allow unambiguous identification. Where unknowns are not in the library, the Discover can be combined with mass spectrometry to aid partial or complete structural elucidation. Furthermore, the disk is indexed, allowing rescanning or over-deposition to increase signal-to-noise of the entire deposited chromatogram, or, in the case of rescanning, specific chromatographic regions. Whilst the Discover does give a concentration-dependent response, it is typically installed with parallel analog and or mass spectrometric detection. This schematic provides a more detailed illustration of the principles on which the DiscovIR-GC operates. The GC column passes into the vacuum chamber of the analyzer, indicated by the dotted black line, through a heated interface. The column eluent is then deposited onto a rotating infrared transparent zinc selenide disc. Deposition occurs through condensation of the vapor phase analytes onto the disc, which for GC applications is typically cooled to -40 degrees C. A focused infrared beam, which enters the vacuum chamber through salt windows, then passes through both the disc and the condensed sample. after which it is refocused onto an MCT chip in the detector, with a solid phase infrared spectrum being collected at approximately every half a second. Condensing the eluted peak provides several advantages over the older light pipe technology. Firstly, converting the eluted peaks from the gas phase into the solid phase greatly concentrates the sample and increases the sensitivity of the technique. And secondly, at 4 reciprocal centimeters, solid phase spectra deliver superior selectivity and specificity compared to gas phase spectra. At this stage, it's worth focusing on the deposition onto the zinc selenide disc in a bit more detail. At 10 centimeters in diameter and 2 millimeters thick, it's slightly smaller than a DVD or compact disc. In this illustration, the green spot represents a peak that is condensing onto the disc which is rotating counterclockwise. As the disc rotates, the deposited peak moves towards the infrared beam. As the deposited peak passes through the beam, the instrument records solid phase transmission spectra, and the entire chromatogram is deposited onto the disc as a continuous track. As the disc is indexed, it is possible to rescan deposited peaks or over-deposit repeated injections of a sample. Both approaches increase the detection limits attainable with low concentration samples by improving the signal to noise. Signals are additive, noise cancels out. If we move from schematics to a photograph of the vacuum chamber, the capillary is located on the right. As components elute from the column, they're deposited onto the rotating zinc selenide disc, recording in a similar spiral manner to the groove on a vinyl record, using liquid nitrogen to condense the GC eluent. Transmission IR analysis is then done in real time on the deposited track. With the basic configuration shown here, the DiscovIR-GC is coupled to an Agilent gas chromatograph with automated liquid sampler and parallel FID detection. The standard configuration for forensic drug analysis is a little more advanced, with the DiscovIR-GC and mass spectrometer coupled to the GC in parallel with a simple post-column split. Data acquisition is through a single sequence table in the GCMS instrument software, with the DiscovIR-10 software set to follower mode. GCMS and FTIR data are acquired in matching timestamp data files. Combining the two detectors provides complementary data for peak identification using spectral libraries. The post-column split for an Agilent MSD is shown here. The column is split at the MSD interface using an unpurged T-splitter. The MSD is installed in line with the rear inlet, and the Discover interface is in the front inlet position. The DiscovIR-GC is easy to use with a similar data structure to GCMS and a user interface that will be familiar to existing GCMS users too. For forensic drug analysis, the DiscovIR-GC fits into existing lab workflows and delivers high-resolution, library-searchable FTIR spectra that are compatible with existing ATR and transmission libraries. The DiscovIR-GC is available as a complete solution or as an upgrade to any existing GC on the market. Looking beyond forensic drug analysis, the DiscovIR-GC has applications in chemical weapons analysis, agricultural and crop sciences, and food, flavours and fragrances. All applications requiring the routine identification of compounds in complex mixtures and matrices. There are several reasons to choose DiscovIR-GC. Ultimately, they all derive from the fact that, compared to mass spectrometry or gas phase FTIR, every compound has a unique solid phase infrared spectrum. This means that library searches are unambiguous. In addition, FTIR is the only spectroscopic technique with commercial libraries of similar size and coverage to mass spectral libraries, and many customers will have libraries of their own raw materials and finished products. This allows routine, unambiguous identification, even for structural, positional, and diastereoisomers, where a reference spectrum for the compound exists in the library, even in complex mixtures and complex matrices. Furthermore, For unknowns, infrared spectra contain structural information that can be combined with mass spectral information, including molecular weight, formula, and fragmentation data, for partial or complete structural elucidation. For many applications, mass spectrometry is the right tool for the job. But direct deposition, hyphenated FTIR, is a powerful technique to add to the toolbox where unambiguous identification is required, or for the identification of compounds in complex mixtures or matrices. I'd like to illustrate the power of the DiscovIR-GC using a simple worked example, the identification of xylenes and ethyl benzene. The mass spectra are both virtually indistinguishable and simple. They do, however, contain important useful information. We can determine the molecular formula from the molecular ion and isotope pattern, and the base peak at mass 91 confirms the presence of a benzene ring. We can therefore conclude that all four spectra are alkyl substituted benzenes with either one ethyl or two methyl substituents. In this case, the FTIR spectra are in the libraries, and at 4 reciprocal centimetre resolution, the spectra can be readily differentiated with library search algorithms. And there are key differences in the fingerprint region too, that allow the contribution of co-eluting pairs to be determined. But let's imagine we didn't have FTIR. What would the alternatives be? Well, we could do preparative GC, concentrating and collecting fractions for NMR. Or we could buy or synthesize the 4 possible isomers and co-inject them to confirm a retention time and mass spectral match, provided, of course, we're using a separation that yields baseline resolution of all the isomers. In this example, both approaches are comparatively straightforward, as there are only 4 possible candidates. But if we move to monoterpenes, increasing the size of the carbon skeleton by just 2 carbons, for each molecular formula there are tens to hundreds of possible isomers, many with virtually indistinguishable spectra, only some of which are in commercial libraries. Here, even with multidimensional chromatography, any identification is only partial, and there's a significant possibility of misidentification. By comparison, searches against GC-IR libraries are still partial, but they are unambiguous. That concludes my part of today's webinar. Thank you for listening, and I'll hand over to Tracy now.
Hello everyone, and welcome to our presentation. I'm Tracy Philpott, Senior Applications Chemist for Spectra Analysis Instrument. DiscovIR-GC uses the power of infrared spectroscopy to distinguish between positional and structural isomers of various controlled substances. In the past, these have included pseudoephedrine, ephedrine, synthetic cannabinoids and cathinones, among others. Today we will focus on fentanyl isomers and analogs. We'll look at the traditional identification tools for drug substances and the use of infrared detector for identification. I'll introduce the DiscovIR-10 software, and we'll close with the benefits of GC-IRD and mass spec in tandem. Here are some of the CDC statistics from 2022 on the opioid overdoses. An increase in overdose deaths from synthetic opioids was noted in 2013, and the opioid crisis was declared a public health emergency in October of 2017. That declaration has been renewed every March since then. The CDC reports an almost 4-fold increase over the last 5 years in drug overdoses involving fentanyl. Of the nearly 110,000 overdose deaths in the U.S., about 2/3 of them, 75,000, involve synthetic opioids. Overdose deaths in adolescents is rising more rapidly than in the general population, nearly doubling each year. That number was just over 2,000 last year. Fentanyl is now a leading cause of death for young Americans between the ages of 18 and 45. This is the molecular structure of fentanyl. Note the methyl group on the propionamide group. In this webinar, we'll discuss the use of infrared and mass spec in the analysis of some of the fentanyl isomers and analogs created by changing the placement of this methyl group to other rings on the structure. We used a typical screening method for the analysis of these isomers. The HCl salts of these isomers were prepared in methanol at a concentration of 400 parts per million. The salt was cleaved in the GC injector. Separation was performed by injecting 1 microliter of solution onto a DB35 MS with dimensions of 15 meters by 0.25 millimeter ID and 0.25 micron phase. The flow rate was 2 mils per minute. The injector temperature was set to 270 C. A split of 5:1 was used. The initial temperature was 225 C, ramping at 30 degrees C per minute to a final temperature of 300 degrees C for 10 minutes. The DiscovIR heated zones were placed at 280 C and the zinc selenide disc was cooled to -40. In 2021, the DEA placed orthomethyl acetylfentanyl in Schedule 1 of the CSA. These fentanyl isomers pose an imminent hazard to public safety due to their abuse potential. In this slide, we see the positional isomers of methyl acetylfentanyl. The position of the methyl group is located at the ortho, meta, and para positions of the methylphenyl ring of the acetamide core. In the GC chromatogram, we see that orthomethyl acetylfentanyl and metamethyl acetylfentanyl have overlapping retention times at 4.32 and 4.33 minutes. The paramethylfentanyl has a retention time of 4.54 minutes. It's only 0.2 minutes later than the other two isomers. Using the standard analytical technique of mass spec for detection, the three isomers cannot be distinguished by their product ion spectra. The molecular ion is 336 m/Z and is barely discernible. All have a base peak ion at 245 with the same fragmentation ions at 202, 160, and 91 m/Z. There are no differences in the mass spec of the three isomers, making it difficult to positively identify any single isomer. This is the solid phase transmission infrared spectrum of orthomethyl acetylfentanyl by DiscovIR-GC. The spectral resolution is 4 wave numbers, and the spectral range of DiscovIR is 4,000 to 700 wave numbers. Let's look at the solid phase transmission spectra of the three isomers by DiscovIR-GC. I've stacked the spectra of the isomers here. While they're similar in the methyl, methylene, and amine regions of 2700 to 3100 wave numbers, there are differences in the fingerprint region below 2000 wave numbers. Here we have zoomed into the fingerprint region below 2000 wave numbers for the stacked spectra. Different spectral characteristics for the three isomers are highlighted in yellow. There are several unique peaks in each of the isomers, along with wave number shifts of 4 to 8 reciprocal centimeters. Peak differences are clearly seen in the fingerprint region when the spectra are overlaid. These include 1515 and 831 wave numbers in the para isomer, 779 and 725 in the ortho isomer. Additionally, we see wave number shifts at several points in the spectra of all the isomers. These are essentially in the 1600, 1250, and approximate 1075 wave number region. These shifts of 4 to 8 wave numbers will distinguish the isomers in a library search. Using DiscovIR 10 software, the FTIR library search shows the discriminating power of a first derivative search for orthomethyl acetylfentanyl. The best match is the ortho isomer with a large discrepancy of 14% between the first and second closest match. The remaining 4 matches have a molecular weight of 336 and the same formula weight, but are much lower in hit quality. The overlay of the orthomethylacetofentanyl to the acetofentanyl in the right-hand pane, which is a second match, shows spectral differences between the two synthetic opioids. We've compared methylacetofentanyl where the methyl group was at various locations on the phenyl ring. Now we'll take that methyl group to the phenylethyl ring, the 2', 3', and 4' positions. In the lower right-hand corner, we have fentanyl. We've brought that in to show you, again, that the methyl group is attached to the propionamide group in fentanyl. This slide shows the mass spec of the three analogs. Although the molecular ion is still 336, the base ion peak is now 231, with fragmentation ions at 188, 158, and 146. The mass spectra are identical and would be inconclusive for identification. Here are the solid phase transmission spectra obtained with DiscovIR-GC. The fingerprint region below 2000 wave numbers is displayed. When the IR spectra of these analogs are overlaid, we see wave number bands specific to each compound. These include the 1612 in 3', 1517 in 4', and 1760 in 2'. These unique differences will be apparent in the library search of the compounds. This user-created library in DiscovIR-10 software contains isomers and analogs of methylacetofentanyl, along with fentanyl and other fentanyl compounds. Once again, we see the discriminating power of a first derivative search for 2' methylacetofentanyl. The best match is the 2' analog, with discrepancy between the second and third match of 3' and 4'. The difference is 2% and 3% respectively. The remaining 4 matches are much lower in hit quality. In the right panel, we've overlaid the 2' methylacetofentanyl and the 3' methylacetofentanyl, which is a second match, and we see the spectral differences between the two analogs. Let's compare the two detectors of mass spec and infrared. There are subtle structural differences in isomer molecules. Mass spectrometry determines the molecular weight and the formula weight of a molecule, but sometimes compounds have the same molecular weight and the same ion fragmentation pattern, making identification difficult. Infrared spectroscopy identifies the functional groups in a molecule, and as functional groups change position in the compound, unique spectral features are identified. The DiscovIR-GC detector provides high-resolution solid-phase infrared spectra to differentiate between the isomers. And by joining the strengths of these two detectors, the characterization of unknowns is easily performed in a single analysis. DiscovIR-10 software for DiscovIR-GC allows for simultaneous data collection and analysis. QC checks are stored digitally. Setup and run allows the user to set up, start parameters, and move on to other analysis. DiscovIR will automatically start when those settings are met. Follower mode allows any GC to control data collection. In library searching, all selected peaks in a chromatogram can be searched simultaneously against multiple libraries. We have partnered with Wiley Science Solution to offer select spectral databases. Report templates can be customized by the user. With DiscovIR-GC, we are able to integrate infrared and mass spec into a single analysis. As shown earlier, DiscovIR can be integrated with mass spec using a simple post-column flow split for tandem analysis. The GC mass spec sequence controls the data collection without the need for multiple sequences. DiscovIR-10 software set to follower mode allows DiscovIR to operate as a parallel detector with a timestamp data which correlates to GC mass spec data. Follower mode allows the user to set up sequences on their preferred GC. An additional selection enables the continuation of GC runs without Discover data collection. Once set to follower mode, the user opens the Setup and Run tab. In the Setup and Run tab, the base information for the sequence is input, including the stop time of the longest run. The selection is saved, and a sequence is created on the GC. That sequence is saved and started. Methods of varying length can be used in the sequence, and an external event setting in the GC method will trigger the end of the Discover data collection. Once the Collect IR Data button is pressed, Discover will continue to listen for any inject signal and begin data collection. This will continue until the disk or the MCT detector warms up. When that happens, Discover will be placed into a safe standby mode. And if the Allow GC Injections after End of Following option was pressed in Toolbox, the GC mass spec will continue to run without Discover data collection. Now let's summarize the benefits of coupling DiscovIR-GC to mass spec detector. The DiscovIR-GC system is capable of obtaining high-quality IR spectra with excellent resolution and signal-to-noise. The two detectors working in synergy provide data-rich and structural information, allowing for rapid identification of complex mixtures and isomers. The DiscovIR-GC system is an effective tool in the identification of closely related compounds and offers an excellent complementary technique to analysis routinely used in forensic laboratory. I would like to thank Cayman Chemical Company for providing the FAS kits. Their newest FAS kit, Emergent Drug Panel, expands forensic laboratory capabilities to the detection and identification of additional emerging drugs of abuse that are commonly found as co-drugs in fentanyl-containing samples. We appreciate your taking the time to attend this webinar, and at this time we are happy to take questions.
Thank you very much, Nathan and Tracy, for sharing your expertise. Okay, we're now to start the live Q&A session. We'll get through as many questions as we can. So, number one, what is the disk space chromatography hours?
I can answer that. Yeah. So with our disk space, as Nathan said, it's a zinc selenide disk, and each track is separated by 1 millimeter. So typically we're running a disk speed of 6 millimeters per minute, and that's approximately 20 hours of runtime. The disk can be slowed down to increase the amount of space available on the disk. And by slowing down the disk speed, you're able to increase the abundance of your deposit.
Great, thank you. Next question is, what is the lifespan of the disk?
I'll answer that one. The lifespan of the disk is effectively infinite. Small scratches don't really matter, so it should one disk should last the lifetime of the instrument. Obviously, if you drop it, it is brittle, so if you drop it, you will need to buy another one, but the disk should last the lifetime of the instrument.
That's great, thank you. How about the frequency of collaboration?
Oh, calibration? Yes. So Discover has built-in tests. The forensics all differ by the intervals of calibration, and those can also be set in the Discover. So you can set the interval that you're going to test, the voltage, the noise, and the wave number check on the system. Typically, the voltage and noise are very quick tests. The wave number check with polystyrene just takes a few minutes on that. Most often the labs will do that as a daily check. Some do it as weekly. So it's up to the labs to set that, but it's very easily set in the software.
That's great, thank you. Next question, what library formats are compatible with Discover 10?
For the Discover 10 compatible libraries, there are several that are compatible. There's the Thermo Fisher, Aldrich, the Biorad, chemical concepts, and which include the Hummel libraries. We also have a relationship with Wiley, the know-it-all software, and the format of Discover It is a .spc format, which can also be pulled into third-party softwares like 5-Ash Data Management, and as we said, the Wiley know-it-all software.
Great, thank you. What is the smallest compound that can be measured with DiscovIR-GC?
Do you want to answer that one, Tracy?
You want me to do this one? Okay,
Yeah.
Very good. So with Discover, we're cooling to 40 degrees C. We actually can cool lower than that to to minus 40, and then we could cool lower to minus 50 C, although you would need to be sure you have a leak-tight GC system. But our smallest molecule is typically 7 carbons. The heptane we can see down at the minus 40, minus 50. Many of our customers are actually using decane as an internal standard on that. So we can do very small molecules.
That's great, thank you. Can specific wave numbers be scanned with Discover?
Nathan, I'll take that one too.
Yeah.
I'm taking them all. No. So with the wave number scanning, we actually, with Discover 10, we have a 2D contour plot. And in that contour plot, we see the wave numbers versus time. And then over that contour plot, we see the different abundances as a color density. So just by a screening technique, you can easily see where the concentration of deposits are within the wave numbers. And additionally, we have crosshairs that you can center over a specific wave number to see where those retention times match up. So with data collection, we have a screening technique where we can look at specific wave number bands within that deposit.
That's great, thank you. Is there a trial version of Discover 10 that's available, and how much LN2 is required for it?
Oh, okay. So we do have a trial version of our Discover 10 software. It's available on our website. I believe it's 45 days, so it can be downloaded. Gives you it's only to do data evaluation. If you do not have a Discover, you cannot run your Discover with that. But it's a good opportunity to take a look at a library searching and data analysis of some of your current samples that you have with that. And then for the amount of LN2, Nathan, did you want to answer that one?
Yeah, so the liquid nitrogen dewar for the cooling the disk is a 10-litre dewar, and then the MCT detector is a litre, isn't it, Tracy?
Yes, it takes about half a litre, but usually some is consumed in cooling.
In cooling. So that will last 18 hours overnight, typically for a run. And then the only thing you need to know is you need to have the dewar for cooling the disk empty if you are ejecting the disk for routine maintenance.
That's great, thank you both. Do you anticipate providing a similar detector for HPLC?
Yes, in fact, we have a DiscovIR-LC that is used for both reverse phase, so HPLC applications, and GPC applications. Currently, we're using it for polymer identification. So a lot of times you're looking at perhaps a single comonomer, its distribution across, or its concentration and chemical composition across a molecular weight distribution. So yes, currently we do have that. We are actually in development for some advancing the technology of the DiscovIR-LC. So
that's great, thank you. How do you clean the disk and make sure there isn't carryover?
Nathan?
Yeah, so cleaning the disk is fairly straightforward. You eject the disk and then wipe it with an organic solvent of your choice. Generally, there's no carryover as long as the disk is thoroughly cleaned.
That's great.
And I'd like to if I could expand on that,
Yeah.
many of our forensics laboratories, they have they use a process of running the blank first, followed by the sample. And one of the things about Discover is that you can deposit over a previous sample. So Discover tracks each track pointer. So all of that data is compiled so that you can place two successive runs over each other, and that helps you determine that the disk is clean before that sample actually is deposited over it.
That's great, thank you both. Would it be able to distinguish stereoisomers? DL methamphetamine is a problem with MS.
Yeah, so you can't distinguish stereoisomers directly from the FTIR spectrum, but you can do chiral chromatography, either with a chiral column or using chiral derivatives on a normal column. So if you are looking to distinguish DNL methamphetamine, there's the potential to look at a chiral derivative. So run your normal drug screen on a standard non-chiral column, and then if you want to characterize the DL methamphetamine, do a chiral derivatization, which will then give you chromatographic separation of the peaks.
That's great, thank you. Is it possible to analyze volatile compounds?
So I think Tracy's covered that one with the lowest molecular weight, the lowest carbon number we can analyze on the Discover. So yes, we can work with volatile compounds, but we have got that sort of C7 cutoff in terms of volatility on the FTIR. However, for unambiguous identification below C7, you typically don't need the FTIR to be able to do that, because we've got enough chromatographic space and a relatively small number of candidate isomers to be able to identify from the GCMS without requiring the FTIR.
That's
Assuming
great.
we've got parallel mass spec, of course.
Yes, that's great, thank you. I think we have time for just one final question. So how much separation between GC peaks is necessary for accurate FTIR data?
In principle, you don't need any separation. It depends on how similar the spectra are. So if you've got two spectra that are very, very similar and have very little or no difference between them for co-eluting peaks, then it's going to be more of a challenge, but typically that's not generally a problem. So if you've got a unique wave band, for taking the xylenes as an example, you can do an extracted band chromatogram of the peaks that are unique to that compound in the spectrum, and then you can quantify co-eluting peaks on that basis. You can go beyond that and use mathematical algorithms, so you can use simultaneous equations, multiple linear regression, or deconvolution, and Know-It-All has a mixture analysis component within the software that will allow you to look at effectively deconvolve peaks that are in the library. So if you've got co-eluting peaks and one or more of those components are in the library, you'll be able to do mixture analysis, and then if you've got an unknown co-eluting under that, you've got the potential to be able to look at the unknown and pull out the unknown spectrum as a residual spectrum after a subtraction of the known components. Do you want to add anything to that, Tracy?
No, I think that's very well done. Thank you.
Great, thank you Nathan and Tracy for answering all those questions for us. Unfortunately, that's all we have time for today, but if your questions haven't been answered live here, then don't worry, because we will pass all the questions over to our speakers and they can follow up via email. If you wish to revisit the topics covered today, then this webinar will be available on demand for the next couple of days. Thanks again, Nathan and Tracy, and thanks to all of you for attending. I look forward to seeing you all at future webinars.
Thanks,
Thank you very much.